So this lecture I have prepared, it's basically an introduction on molecular dynamic simulations. It's going to be 1 hour. Typically, to fully learn molecular dynamics, you would definitely need more time than 1 hour. So my intention would be to give you some background about this simulation technique and, and talk about like the connections to the overall course on the mathematical modeling of complex fluids and flows. So let me also mention that if you're interested in the molecular dynamics approach, then there are two very well-known standard books covering this topic. One is by Allen and Tildesley. The book is titled Computer Simulation of Liquids. There is a recent version of the book which has appeared in 2017. And there's one more book which is by Frenkel and Schmidt titled Understanding Molecular Simulation, which was published back in 2001. So what I'm showing here is it's supposed to be a movie. I don't know why it's not playing, but basically this is actually a molecular dynamics simulation showing particles which are moving around. And in MD, typically we have about 1,000 to 100,000 particles. Of course, you can go slightly higher to maybe million or closer to billion nowadays, but those are excessively large simulations. And most commonly, the system sizes which will be handled are about 100,000 particles. And the time scales which are accessed are fairly short, which is from 10 to the power minus 15 to about a microsecond. So if we think in terms of typical materials we deal with or the fluids we talk about, the scales are completely different, right? Of course, we work with Avogadro number of particles with most material samples, and the time scales mostly are in the range of seconds to minutes. So the main purpose of this talk is to show like how MD with all these limitations in the length scales and time scale can still contribute to our understanding of fluid flow and fluid properties. So let me kind of connect you to the general understanding. In nature, of course, we come across fluids very frequently, and here are some examples of fluid which are flowing, and some of them the flows are quite fast, others the flow might be slightly on the slower scale. So to explain all these systems, the standard approach uses the Navier-Stokes equation, which can describe viscous flow at macro scales. And if you look at this equation, this is like an equation having time derivatives as well as spatial derivatives. And there are certain material properties that appear, namely the density and the viscosity. And there are other parameters which I'll call as control parameters. Those could be like velocity flows, which we might impose, or there might be pressure gradients, and there can be a temperature which is imposed. And so knowing these control parameters, that kind of decides the material viscosity and density, which eventually is used in Navier-Stokes equation to solve for the fluid flow. And if we look at the material property itself, here we're looking at the viscosity part, which is typically understood in terms of a stress versus strain rate plot. We know that there can be different kind of behaviors which can be encountered, and these are typical viscous models which are used extensively. So if you were to estimate the viscosities, for instance, a common approach would be to experimentally determine this using a rheometer, and then passing that parameter value to the Navier-Stokes equation. And this can be done for tens and hundreds of different materials for different fluids. But imagine if we were to work with thousands or even more number of fluids at a time, and we wanted to predict what the viscosity would be or how the density would vary with temperature and pressure, that becomes a challenge to do experiment. So can we make use of our understanding of the molecular structure, the molecular makeup, and predict the macro scale properties? So if that is the kind of question you have in mind, then molecular dynamic simulation is a very powerful tool to start from the molecular scales and predict the material transport properties and thermodynamic properties. So, these are like two options which I'm showing for determining the viscosity using molecular dynamics. So I have not explained what MD is, but I'm trying to set the stage that why one should be interested in molecular dynamics. And there are two options. The first option is one can use what are called Green-Kubo relations, which state that the viscosity can be determined by evaluating how the stress varies with time. So if you notice that this is a time integral, and we have the stress terms, right? And stress, you know, is a tensor, a matrix. So typically we have to specify two indices, and here we're looking at the cross terms in the stress tensor, and we have the stress at x and z at time 0, and the same stress at time t, right? So this kind of a quantity is called an autocorrelation function. It's a time correlation function, and we need to integrate over time these different terms to estimate the viscosity, right? So it's a fairly straightforward equation. All we need to know is how the stress might vary within the fluid system, and for this one can use equilibrium molecular dynamics simulations, which I'm going to talk about in the next few slides. And basically we're going to perform MD at a desired temperature and pressure, and then compute from the MD calculations these stress tensors, and from the stress tensor information then compute the viscosity. The other option is to perform an MD simulation just like the experiment, right, where you apply an external shear and you make the walls of the system essentially move, and measure the velocity profiles at frequent intervals, and this will provide an idea about the strain rate which is there, and one can therefore compute the viscosity, right? So there are these established methods which are available, which can provide us with the viscosity estimates, and all we now need to do is to have a formalism where we can start from the molecular scale properties and estimate the stress value or the strain rates and so on. Okay, so if you want to think at the molecular scales, we know that all materials are made of atoms, and so if you look at this glass of water, you can see that the water is moving within the glass because of this inflow present. And if you were to take a fluid packet, you would be able to note how it moves. Okay, so this velocity of the fluid packet is basically related to the kinetic energy of the packet, and I'll have this subscript external being used to describe the overall energy of the packet. There is also a potential energy of the packet because there is a gravitational field. So that also comes into picture. And the total energy of the system is basically a combination of the potential energy and the kinetic energy. But if we were to look inside the packet at the molecular scale, remember that this entire packet is moving together in some sense. There might be some fluid particles entering and leaving also. But by and large, the packet is moving inside the glass. And what you would find is internally, the molecules would be vibrating and colliding with each other, and there will be some motion of these molecules. So this internal energy is something which we would like to compute with molecular dynamics. So molecular dynamics will uh, uh, inform us about the total kinetic energy internally and the total potential energy internally, where the potential energy means the interactions between molecules, those will be computed, and the total internal energy, which in thermodynamics we encounter frequently, is the sum of these potential energies and kinetic energies, right? And so this total sum has to be evaluated for all the atoms present within my small fluid packet. Okay. What I'm going to show is that there are models which are available, which can be used to evaluate the potential energy, at least the internal part. And these interaction models capture the bonding within a molecule, as well as other non-bonded interactions when two molecules are interacting with each other through charge interactions or through some van der Waals dispersion interactions. So those terms can be accounted for in these interaction models, and we can compute the potential energy. And with regards to the kinetic energy, if we were to note the velocity of every molecule, every atom in the system, then the classical definition of the kinetic energy is basically half mv square, where v is the velocity of the particle, and we have to add up the kinetic energies of all the atoms in the system. Okay. Finally, we know from thermodynamics that different forms of energy can be exchanged or interconverted, right? So internal energy can be converted into external energy or vice versa. And so molecular dynamics can account for all these aspects, and it can be used to calculate the thermodynamic and dynamic properties. So here the movie is playing. This is a molecular dynamics simulation showing how particles are moving around. So as I said, in MD, we work with atoms, and atoms are represented as point masses. Okay? So every dot is a single atom, and the dimension, it's basically a single point. And these points will move. So we're going to track the position and velocity, and these atoms will interact with each other. So the model which is used is basically Newton's equation of motion is used in MD. And according to Newton's equation, the force acting on a particle I is equal to the mass of the particle times the acceleration on the particle. So we know that at the macro scales, this equation of course works, and I'm sure most of you would have applied these equations at even in your 11th standard and 12th standard by solving for the motion of projectiles. The same equations can be used to study how atoms and molecules move. Right? Every atom which is present would have a mass, and we know the atomic masses quite well. And the forces have to be evaluated. If the forces are known, then the acceleration is available to us. Okay, and the rest basically involves solving this system of ordinary differential equation. The first set of equations basically tells us that the rate of change of position is basically the velocity. And the second equation tells us that the rate of change of velocity is the acceleration, right? So if the right-hand side terms are known to us, then one would have to just solve for the position and the velocities in time. And they're going to be n atoms, and every atom, remember, has the x, y, z coordinate. So there will be 3n equations which are present. These will be coupled because of the interactions between the particles. And there will be 3n velocity evolution equations. So a total of 6n equations have to be solved. So imagine if n were 1,000 atoms. So at a time, we will be solving for 6,000 equations simultaneously. And this is a fairly large exercise. And typically, one can reach up to million atoms on the standard workstations which are available with each of us. So molecular dynamics is a numerical simulation technique that solves for the motion of atoms and molecules over time. The forces are computed at every step because we're going to do some time stepping. So we're going to have a discrete time delta t, which will be used by numerically solving these equations. And at every step, we're going to compute the forces to find the acceleration and then update the positions as well. So we compute the forces at each step. The velocity and positions are computed in small time increments of delta t. And with all this fluid motion, we can understand how molecules interact with each other. So if there are viscous drag terms, then we can, by looking at the motion of the atoms, identify the drag forces which are present, which gives us something like a viscosity. Or one can also compute the density. So if you specify the temperature and pressure and let the system relax, then we can determine the total volume of the system, and knowing the total number of particles present, the density can be obtained in that way. Right? And molecular dynamics nowadays has become extremely popular because when it comes to the complex fluids where there's a lot of structure which can be present. So for example, you can have colloids present or particles present, or you might have different types of surfaces and interfaces present, or polymers present, and charged species also present. Then molecular dynamics gives you, it's almost like a microscope, which can show you how these systems evolve in time. Right? So a lot of groups are using molecular dynamics for gaining those kind of insights. So let me talk about how we typically model the interaction between particles. I would use the word particle and atom interchangeably, because in MD we are basically solving for the position of these atoms. If you consider water molecule, we have 2 hydrogen and 1 oxygen. There are these bonds which are present. And from first year chemistry courses, you would know that in water, there is a particular angle between the bonds, and there is a certain bond length which is present. So during the dynamics, the bond length can fluctuate. So you can have the OH bond actually shrink and expand, right? Contract and expand. And a common model which is used is a spring model. So we treat this bond to be like a spring, which has some equilibrium length R naught. And we basically find the spring energy associated with the bond. So all you have to do is to determine the spring constant K subscript R to get the bond energy as a function of the length which is there. If the bond is stretched extensively, then this quadratic term grows. If the bond is contracted, then also the energy term grows. Only when the bond length matches with the equilibrium bond length, we get a 0 contribution from this term. In a similar spirit, we can consider the angle, bond angle term. And even though the equilibrium bond angle is around 104 degrees, when the molecule vibrates, there are these different vibrational modes, which can cause the angle to depart from this value. And so we consider a spring-like expression for the angle as well, where theta naught is the equilibrium angle for the molecule, right? And with that, we have a basic kind of covalent model available for our molecule. Is there a question? Okay. But if you consider other molecules, for example, here we have a carbon-based molecule, and typically, there might be some sort of a backbone which is present. So you might remember from your early chemistry days that the backbone typically has an angle, and you can get these trans and gauche conformations. So what might happen is around a particular bond, the rest of the backbone might rotate, and there might be these different angles which are obtained based on the conformation. A nice way of thinking about this bond is you can imagine like a book which is open, and we have the bond basically placed at the center of the book, and the other connecting bonds along the backbone, they are present on the 2 pages of the book, and we can change the angle between these pages, and that is called the dihedral angle. So depending on the movement of this phi angle, the dihedral angle, you would get some steric interactions between different parts of the molecule, and that can be also incorporated, right? And finally, we have these non-bonded interactions, because it's not just looking at within a molecule, but also between different molecules. So they can interact through dispersion interactions like van der Waals interactions, or there can be charges present on the molecules. So one would incorporate a Coulomb's law to capture the interaction between the ions. So in general, the molecular system is composed of many molecules. Each molecule has bonds and angles and dihedrals, and there can be non-bonded interactions. And we have to add up all these contributions to get the total potential energy of the system. Any questions as of now?
I have one question, which is like,
Yes.
how is the angle like compared to stretching and compression? Because it's at an angle and it's not linear.
Yeah, so you can imagine, taking this water molecule and twisting it in different ways. Okay, so the angle part assumes, basically considers this angle between the HOH, right? O at the vertex, and that is one particular angle which you may have. And so when you twist the water molecule, the energy of the water molecule will change with the hydrogen and oxygen positions. And these energies can be calculated either quantum mechanically using density function theory or some other accurate technique, or spectroscopically also one can evaluate some of these quantities. And so those energies might be known from like these electronic calculations, and so one would parameterize the bond spring term, the spring constant, using such energy data. Does that answer your question, Ranil?
Yes, someone. Thank you so much.
Yeah. Okay. So the bottom line is, I mean, typically, these parameters are tabulated for a lot of molecular systems, whichever system you are interested in. There's a good chance that in literature you might find these parameters, and so all you have to do is to pick up the model and prepare different configurations of the system. The positions of atoms might change, molecules might change, and you would be able to evaluate the potential energy of the system. Okay. Now, in molecular dynamics, we want to solve Newton's equation of motion. So we want to solve for the force And the way the force is evaluated is through the potential energy. So we basically, let's say we want to calculate the force acting on this hydrogen atom in the x direction. And we have a certain configuration. So all the water molecules are present at their own respective places. And we're looking at a snapshot of a system, right? So the molecules are basically all fixed, frozen in space. Positions are well known. And the way the force will be calculated is if we were to nudge this hydrogen atom to the right along the positive x direction or to the left along the negative x direction, and then compute the potential energy, we'll find that the potential energy has changed. The bond lengths have changed, the angles have changed, non-bonded interactions have changed. And so there will be a delta E change in energy for the delta X change in position we have introduced. So the force on atom I in the X direction can be computed basically as a derivative of the energy. And there is a negative sign which you have to keep in mind always. And in general, for a system of atoms, the forces can be computed as a negative gradient of the energy function, the potential energy. And basically that involves computing, in the similar kind of manner. For every atom, you displace it in the x direction, in the y direction, in the z direction, and you compute the forces. So there will be 3n force terms because there are n particles, and each particle will experience a force in 3 directions, and all those components would have to be evaluated. Okay, now that we have a force at the given position, we can very trivially compute the acceleration knowing the atomic masses, and the velocity, if it is known initially at least, or at least in the last time step, then we know completely the right hand side. We just have to time integrate this equation. So an important consideration is that initially, remember this is a system of ordinary differential equations. So you need to specify the initial condition, which will be the initial position of all atoms and their initial velocities. Okay, an initial position of atoms is fairly easy to set up because you have molecules and you know exactly how you might want to arrange the molecules. So there are these are like standard techniques which one can easily search for and figure out how to place molecules in a desired kind of structure. But essentially we will generate some initial configuration like this where we know where every atom is present. And the velocity I'm going to talk about in a moment, that how we can initialize the velocities. And then subsequently, once we have these initial conditions, then we need to time integrate. And there are these different kind of schemes which are there, different schemes mostly. For example, there's a numerical technique called Euler method. And then there are other techniques like Worley method and leapfrog Worley method, which are different time integration schemes which can be used to propagate the dynamics. One has to also keep in mind that in molecular dynamics, the energy should be conserved because kinetic energy and potential energy are going to interconvert. And so the energy is constant, the total number of atoms is constant, and the volume also is kept constant. Okay. So as far as selecting the initial velocities is concerned, well, we make use of something called the Maxwell-Boltzmann distribution, which comes from statistical mechanics or statistical thermodynamics, which says that the velocities of particles is distributed as shown here. The distribution depends on the mass of the particles and the temperature. And from this known probability distribution, one essentially samples the velocities and assigns for every atom in the system a velocity. And once that is done, hopefully you can back out and check that the distribution indeed is conforming to the Maxwell-Boltzmann one, and we basically get the initial velocity. So typically we would choose some temperature. So for example, if we are interested in room temperature, then T is the absolute temperature, which will be around 300 Kelvin. And suppose we had water present, then we'll have to consider oxygen and hydrogen atoms. And we're going to assign velocities by sampling from this distribution. And the sampling of the velocities requires use of random numbers. Okay. Those who are interested in more details would have to go to the textbooks I mentioned in the first slide by Allen and Tildesley and Smith. Those books would give you recipes for sampling velocities. And once the velocities are available, then we need to integrate in time. Right? And what we expect during time integration is that the atoms and molecules will start moving. So you can see these dashed lines I have drawn just to show like tiny movements which start to happen. And as you follow the movement of each particle, you would see that it moves in a certain way. So we have to take obviously some time step delta t, which is small, so that the movements are really small. Otherwise, if the time step is very large, there will be numerical errors which will be introduced. So typical value of time step is about a femtosecond, which is 10 to the power minus 15 seconds. And if we were to do about 1 million such steps, then we would reach nanosecond, which is 10 to the power minus 9. And if we were to do about 1 billion of such steps, then we can reach microsecond. And so microsecond is typically the standard time scales you can reach with such an integration scheme. And hopefully with this small time step, you would find that the energy of the system is conserved. If we were to take larger time steps, there will be energy drift, a lot of numerical error, and you might even see big, errors in your force calculation, and that will completely mess up your calculation. Okay, now just a few words about the integrators. Some of these integrators, I'm sure if you have done numerical methods course, you would have come across. For instance, the Euler method is a very popular numerical scheme used to solve ODEs, where you just work with the previous time step which you had and the positions and velocities at that time, and you just march forward by increments of delta t. There are other methods, for example, Worley algorithm, where the time t plus delta t, the positions at that time, are evaluated in terms of the position at time t and t minus delta t. And so clearly there is slightly more memory requirement because you need to store the positions at time t and t minus delta t. And also you need to store the acceleration at the time t, and can basically solve for the positions only. The velocities can be obtained by numerically differentiating the position with respect to time. And there are other algorithms like velocity Worley algorithm, where the time step which is taken is like a half time step delta t. So the velocity can be propagated by a half time step, and the positions can then be propagated by a full time step, and finally you bring the velocity to the time t, and that gives you the final position. I think there should be a t plus delta t in step 3, so you can get the velocity and position at time t plus delta t. And there are other schemes also like leapfrog integration. So typically the velocity Worley algorithm is a popular scheme because it has better numerical behavior compared to some of the other techniques which are used. So overall, the flowchart for molecular dynamics looks like this. We start our simulation by inputting all the initial data like the interatomic potential or the force field to compute the potential energies and forces. provide the initial position of atoms and the initial velocities. And then using this information, we start computing the forces on atoms, update the position and velocity by solving Newton's equation. And then periodically we would collect statistics by storing the positions and velocities. And if more dynamics is required, we'll just continue this process. Okay, so every new position we get, we will evaluate the forces and then continue. Eventually, at some point, we'll have to stop and follow that with the analysis of the data we have collected. So molecular dynamics is fairly expensive calculation. The most expensive step involves computing the forces on all atoms. So imagine if you have a million atoms present and they're all interacting with each other. Just to compute the forces is the hardest part. And updating the position and velocity is not that challenging. But essential requirements typically from an MD simulation would be that we should be performing the simulation as efficiently as possible with low memory footprint and while remaining accurate and having stable numerics. And also if you look at Newton's equation, it is time reversible. So that means if you were to integrate in the negative time direction, then you should get back the same initial position, right? For example, if you were to have a projectile which is moving and you were to reverse integrate the projectile, you will go back to the initial position where the projectile was. The same kind of property is expected with a molecular simulation also. Now, as I said that the most expensive step in MD is computing the forces on atoms. And so a lot of emphasis has been given on how to do the force calculations less expensively. So typically what happens with molecules is if there's a molecule right at the center here, and I were to consider nearby molecules, I would imagine that there will be some interaction present. And as we move away further from the center position, the interactions are going to decay. And that's typically what happens. Beyond a certain distance, the interactions are way too feeble, and there is really no point in including those terms because they're not going to contribute to the total potential energy of the system. So one defines a cutoff radius as denoted by this R cut, and only molecules that are present inside this cutoff radius are included for the interaction calculation with respect to the center atom. Okay. Now, it might happen during your time step that some molecules might move inside the sphere, which has radius of R cut, and some molecules can move out also during the time step. And that becomes an irritation because like every time step you realize that someone or the other has moved in or out. So our list of neighbors can change because of the molecules moving in and out, right? So one typically adds a buffer layer shown by the second larger sphere, the white circle, and that is a slightly extended neighbor. So when we prepare that kind of a larger list, we know that some of these molecules, when they move in or out, they're involving this buffer region. And so the updation of the list of neighbors happens less frequently, right? So there are these neighbor lists like Worley neighbor list and linked list neighbor list, which are used extensively in molecular dynamics to speed up the calculations. One final thing about molecular dynamics is the boundary condition which we need to use. As I said in the beginning, in molecular dynamics, our system sizes are restricted to about maximum million atoms. Usually one would not go beyond that, but million is not that large actually, right? When we consider macroscopic scales. So how do we get a macroscopic like behavior? A common boundary condition which is used is the periodic boundary condition. And this picture illustrates the periodic boundary condition. So in the middle, we have our main system of atoms, and these atoms are moving around. And notice that this system has been repeated periodically in the 3 dimensions in space. Okay, so any molecule, let's say, is moving out of this box, the central box, into its neighbor. Okay, what would be happening is you will have a periodic image have also a similar kind of motion. Okay, that same particle will appear in a periodic box and it will be moving into my central box. Okay, so in a periodic system, everything seems to be repetitive in space. Okay, and any molecule which moves out from the box can be imagined to enter from the other side of the box. Okay, and this is the periodic boundary condition which is implemented. I'm not showing you the numerical implementation, the mathematical implementation, but basically when the particle exits from, let's say, the top part of the box, you make it enter from the bottom part. And so the total number of particles is conserved inside the box. And this gives you an illusion that as if you're working with an infinitely large system, when in fact you have a basic repeat length given by this box dimension. Okay, and this is a very, very frequently used boundary condition in various molecular dynamics packages that are available freely, such as LAMPS and NAMD and BROMAX. Less frequently are these other types of boundary condition, for example, rigid boundary conditions. Here, what is done is we have a system of atoms, and the outer part of the box, we freeze the atoms in it. Okay, so the atoms which are present in this shaded region do not even move, they're frozen. And only the atoms inside, in the inside region, they can move around and they can collide with the frozen atoms. And you basically are interested in the statistics coming from these moving atoms. So this is called a rigid boundary, where atoms at the edge are held fixed. You can have a third type of boundary condition where you have no boundary present at all. Okay, so in that case, the atoms are free to move away if they wish. Now, typically, these kind of boundary conditions might be used. For example, if you have a polymer molecule, right? A polymer molecule, it's just going to drift in space, and there will be a lot of conformational changes, and you can simulate those aspects. Or it could be like a liquid droplet, which is moving in a gas, right? And you don't need any boundary condition really. So the droplet can move around whichever way is required. So, so then this kind of a boundary condition is quite useful. Okay, any questions so far?
Yes, sir. You just explained this.
So I'll move to the last part of this lecture, which is like how do we enforce a temperature or pressure in our system. And so far, the flavor of the molecular dynamics simulation I talked about, the energy is fixed, right? And the volume is fixed. But many a times we want to do simulations at a fixed temperature. And to do such kind of simulations, one typically uses the concept of a thermostat. A thermostat is basically a control setup which would try to modulate the kinetic energy of the system. Okay. Now, from statistical mechanics, it is known that the temperature or the kinetic temperature of a system is related to the kinetic energy. Right. So, if we were to compute the total kinetic energy, then we can determine the temperature. And here, n is of course the number of atoms present, and Kb is the Boltzmann constant, and this equation comes from something called the equipartition theorem in statistical thermodynamics. So if we were to fix the temperature, it basically means that we need to set the average kinetic energy to a certain value. And this can be done by coupling the system to a heat bath and adding or removing energy. If the kinetic energy is too high, we can lower it. We can bring down the velocities and lower the kinetic energy. If the kinetic energy is too low, we can increase the velocities such that the set point temperature is achieved. There are two different classes of thermostats which are used. One of them is stochastic type of thermostat, and then the other is deterministic thermostat. So in the stochastic thermostat, the velocities are randomly altered. So for example, there's the Anderson thermostat, where the velocities of some selected atoms will be resampled from the Maxwell-Boltzmann distribution. Remember that the Maxwell-Boltzmann distribution gives you the velocity distribution at a given temperature. So if we set the temperature and we sample the velocities periodically, then the system can be shown to stay at the desired temperature. Alternatively, a very popular thermostat is the Langevin thermostat, where we basically solve a slightly modified system of equations. The first equation is for the positions, which looks like the standard one. The second one for the acceleration, not only do we have a force term, but we also have a viscous drag term, where the friction parameter is set by us. Typically, this is set to about 10 to the power 12 per second. And there will be an additional stochastic kick term, which will push the atoms in random directions. And so this is to impart the energy. So the kick term will increase the velocity of the atoms, whereas the drag term will work towards reducing the velocities, and together they will ensure that the correct temperature is achieved. Right? And typically one only specifies the friction parameter, and usually the sigma parameter is can be determined from the friction parameters. Okay, and so these techniques, both Anderson and Langevin thermostat, would involve these velocities just changing randomly. Okay, which may be desirable, may be undesirable, because in your molecular dynamics simulation, you might see the particle suddenly change its direction of motion, the velocity, because the velocity has changed. Right. Now there can be another class which is called the deterministic method, where we just can alter the velocities in a deterministic manner. So the simplest approach is the velocity rescale, wherein the velocities is rescaled, meaning it can go up or it can come down by a factor lambda, where lambda is determined by the set point temperature and the instantaneous temperature which we have. Okay, and that would then help us bring the system temperature to the correct value, right? Just by increasing or decreasing the velocities. There are a few other thermostat. The Nose-Hoover I should mention in particular. This is a very popular thermostat, where we add some new equations of motion to describe the coupling to a heat bath, and this third set of equation that would essentially help us bring the system to the correct temperature. We talked about thermostat, but sometimes we also want to control the pressure. And the way in molecular simulations we compute the pressure is through this kind of equation, which contains on the left-hand side, the stress tensor, and on the right-hand side, you basically have an ideal part coming from the kinetic terms, as well as a term from the interaction between atoms. This is called the virial term. So essentially, this is like a force balance being done to evaluate the overall stress which is acting on the system. And this stress is something which you might want to evaluate if you want to study the fluid properties. So it turns out that if you want to have a particular pressure, you want to set the system to, and you find that this right-hand side is giving you a value which is less than desirable, not desirable, then you can basically have a volume change and you can get to the correct pressure. Okay. So basically what is done in case of barostat is we have volume changes in the system. It can be increased or it can be decreased, and accordingly the stresses present in the system would change. For example, if the stress is very high, then we will tend to increase the volume to lower the pressure and the stresses. So these volume changes can be done isotropically, meaning that in all directions the box changes by the same amount, or it can be anisotropic, which means the changes are not uniform. And some of the barostats, the box can even change the shape. So the variety of barostats which are available, and I don't think I have the time to really go through these in detail, but one can basically set the pressure, and one can modify the volume at different time steps based on the set point temperature and get a desired pressure. Okay. So I'm coming to the last part of the lecture, and I need about 5 minutes to wrap up. So overall, when we do molecular dynamics, we can see the atoms in motion. We have the positions and velocity. And statistical thermodynamics gives us tremendous amount of power to evaluate thermodynamic properties and even transport properties. So thermodynamic properties can be like the internal energy. We can compute based on the atomic potential energy and the kinetic energy. And kinetic energies, of course, we can determine based on the velocities. Temperature, we can determine based on the kinetic energy of the system. And here, by the way, I have some angular bracket, which means that we are computing averages for the dynamical simulation. And we can also compute pressure. This pressure equation I showed in the last slide, it's same as this, which requires computation of the virial terms. And one can go on and compute something like the heat capacity and thermal conductivity, and the list is like very long. All the properties that are of interest can be obtained from such molecular system, provided they pertain to the molecular behavior. Okay, electronic properties will not emerge from molecular dynamics simulations. And so we need to compute a lot of these averages denoted by the angular bracket. The average is computed in the standard way. You have to have a number of data points. Here, the capital N refers to data point and not the number of particles. And one can also compute variances and so on. So there is a concept of averaging, like how one can do averaging. So there are two options. One is you can perform multiple MD simulations. So these are, the box shows, one box shows a molecular dynamic simulation. It's a setup, and you can perform a calculation and you can get the position, velocities, other kind of properties from a single MD simulation, and repeat the MD simulation in an independent way. Okay, so change the positions, maybe the velocities, so that the resulting dynamics is slightly different from the previous one. And if you have a bunch of independent observations, then we have basically an ensemble or a collection of independent configurations, and we can report the averaged property of the system. So for example, we can report an average viscosity we can compute across these systems. Alternatively, we can do something called a time averaging, where we perform a very, very long MD simulation, and the MD simulation is so long and we sample very rarely, intermittently. So this way, the from one sample to another, a lot of changes have happened in terms of the evolution. The system has completely changed and it no longer appears same as before. And so we can collect different time points, at different time points, the data, and compute a time average as well. Both ensemble and time average should result in the same thermodynamic properties as well as transport properties. Okay. Finally, since I mentioned in the beginning that typically when it comes to transport properties like viscosity or diffusivity or thermal conductivity, common approach requires the calculation of these autocorrelation function or time correlation functions, where you have a data measurement at time 0 and at time t, and you have to integrate over this time t. This kind of a quantity has to be evaluated. And so typically we need to have two data points separated by this time t. And so we can have a moving window where the gap is kept same as time t, and we can collect a lot of sample points and then compute the average of the quantity, right? So these are like standard calculations, a lot of which has been already automated and implemented in MD packages. And if you're interested, you can use them for your fancy complex fluid system. Okay, so with that, this is the last slide I have. So what I covered in this lecture is a molecular picture of fluids and certain molecular simulation techniques, mainly the molecular dynamics techniques, where we look at interaction between atoms and molecules and study the motion. So with this powerful technique, we can, for example, study how molecules drag each other and compute the viscosities, for instance, using such a Green-Kubo relation. And if one wants to compute the molecular interactions, there are different electronic structure calculations like density function theory and other techniques are there, which can provide the energetics, which will ensure that the molecular modeling can be done in a reliable way. Okay, and in the today's research community, many times uses these different techniques like electronic structure calculations, molecular dynamics calculation, and continuum methods like Navier-Stokes equation in a coupled way, so that they can handle complex fluids. Together with these methods, one can access long length scales and time scales. Okay, so starting from the molecular scale, going all the way up to experimental scales. Finally, there are a class of molecular dynamics techniques called coarse-grained MD, where we don't work with atoms, but groups of atoms. So these are called coarse beads or coarse particles, collection of atoms and molecules, which are made to move together. Essentially, they look like Newton's equation of motion being solved, but here we don't consider the atomic scale interactions. And this forms a mesoscopic simulation technique to bridge the molecular dynamics to continuum model. Okay, so so these are the various concepts I wanted to convey. I know that 1 hour is a very short time to really rigorously go through molecular dynamics, but the intention here was to provide you with all the key ideas and the key terms associated with the MD simulation communities. Those who are interested should definitely take up a longer course on molecular dynamics. And with that, I'll end my lecture, and Professor Tiwari be happy to answer any questions.
Thank you, sir. Is there any questions?
Hello, I'm audible.
Yes,
Yeah, you are.
Pranil.
Yeah, so firstly, just a clarification. So in the time integrators, you had said that the Worley velocity method is a like quite better performing method. Is it because fact that it's implicit and like I get a tridiagonal matrix in this, just like ADI method?
Yeah, so you have partly answered your question. In terms of the numerical error and the stability, if you were to compare with the same delta t, these different methods, you would find that the velocity Worley has all these nice numerical properties. And so based on such comparisons, you would conclude like velocity Worley is a technique to be used. But that being said, you can use any of these other techniques also, provided maybe you choose an appropriate delta t. Okay. But velocity Worley, a lot of the packages by default use this algorithm because of the stability aspects and the error aspects.
One more question is that, so typically I see these are very like short time scale simulations that MD is doing. So typically, how do you validate these? Because experimental time scales are far longer than the ones we are doing in simulations.
Yeah.
So what's the way to?
Yeah, very nice question. So for validation, what you can do is like if you were to take water as a system and you were to perform molecular dynamic simulation, basically look at how water molecules are getting dragged by each other. And from such a simulation, you can compute a viscosity. And then you compare the viscosity to the experimental one. You would find that the simulated values are fairly close to the experimental one. May not match because even by the way, experimental approaches, if you have complex fluid, more complex than water, every type of a rheometer, every technique used might give you a different viscosity at the end. Okay, but if we're talking about orders of magnitude, yes, then the simulation technique should give you a reasonable value, order of magnitude value of the viscosity. Now, with this kind of an approach at the microscopic scale, right, at molecular scale, you're able to see what are the viscosities. Imagine if you had a more complex material, like a micelle system, right, and you ask like, I'm going to have this fluid flow, what is the viscosity of this entire material? Now this technique starts becoming very useful. You can relate the structure to the problem.
Okay, and regarding the rheology part, so like typically rheology is mostly dependent on this, say, molecular or particle architecture. So will DPD perform better than molecular dynamic simulations to envisage diversity?
Right. So DPD in some sense is already coarse grained. Okay. So the molecular interactions are captured in an averaged sense through the use of certain parameters. Okay. Whereas molecular dynamics is more fine grained. So imagine you have some molecular architecture and you want to really in entirety capture, based on this structure, what change I get. I might have a solvent, I have some solute present. What are the solvent-solute interactions? Molecular dynamics should give you more resolved information. And in DPD, whatever effective forces are being provided, those would have come from molecular dynamics in some sense. So MD is more resolved approach. And within the nanosecond timescale you simulate in MD, that is enough to give you the transport properties of interest.
One final question, that is like, how do you correlate these, say, thermodynamic properties which have shown in your last slides from, like, you have shown how statistically we are correlating, but what is the exact procedure by which, like, we are using partition functions? These partition functions are incorporated into these average properties. How do we do that?
Yeah, very nice question. So typically in MD, the partition function would not be computed directly, but rather you're going to compute some observable. Now, what can you observe? You can observe the velocities. You can observe the potential energy, right? The interaction behavior, and that's it. So the trick which is used is just by these two observations, the position and the velocities. By position, I mean also the configurational energy. You will be able to estimate every quantity. So if you were to now look at this list here, the kinetic energy you want to calculate, average kinetic energy of the internal part, right? That depends on the velocities, and velocities I can measure. Temperature depends on the kinetic energy, so therefore I can measure the temperature. If you look at the pressure in the system, okay, or suppose I were to specify the pressure, the corresponding volume will be obtained. Volume I can measure because the positions are available, and I can also compute this temperature part for sure, and I can compute the virial term, which involves again positions and the forces, right? If it comes to heat capacity, the heat capacity depends on the variance of the internal energy, and internal energy is basically the potential energy which I can compute, and the kinetic energy. So I can study the fluctuations in this sum and compute the variance in the potential energy, and that gives me the heat capacity, right? And if we continue like that, any other transport property which you have, like here, this is the velocity, and then this is viscosity, involves the shear terms. The shear basically involves force calculation, and we can evaluate those terms.
Thank you so much, sir.
Yeah.
Hello, sir.
Yes.
Am I audible?
Arun. Yes, Arun, you are audible.
Yes, sir. Actually, sir, I am new to this technique. I just want to know the difference between the finite element simulation and this molecular dynamic simulation. And another question is that can we apply this technique for the impact problem where we can capture the melting and vaporization?
Yes, absolutely. So the impact problems, those I didn't cover, just to keep the top lecture more focused. But yeah, impact studies are done frequently where you're going to have some impactor, usually kind of a rigid set of systems, atoms which are going to impact on your material system and apply a force on the material. That will lead to some indentation or some ejection of material, and you would study the response of the material. So these are used extensively to look at viscoelastic properties, for instance, or if you had a solid substance, then measure the elastic property of the material, toughness, and so on, right? So variety of such simulations can be done. It's only left to imagination, okay? The basic idea is available where you can apply forces and study materials deform. The rest is you construct a simulation setup by which you can measure the positions and velocities, and from that you determine the material properties.
Okay. And so difference between this finite element Lagrangian approach and this approach, what is the difference? So can we apply both this method for solving the same problem? And what is
can you again repeat your question? Which two approaches you are asking?
So can we apply this finite element approach? Generally, we use the Lagrangian approach there, and this technique, molecular dynamics simulation.
So the other approach I still didn't get.
In finite element, we mesh the model
Finite
by
element,
nodes and elements. finite element. Yes, sir.
Good question.
Yes.
So finite element is I would consider that to be like a continuum model, okay, where you would have a lot of these continuum material properties already, right? Available to you. But suppose you didn't have those continuum properties available, what would you do? I mean, option one is you go to experiment and you actually try to measure these parameters, and a lot of times that can be done, but if for some reason it is challenging to do that, then you can move towards the molecular dynamics simulations and get the same parameters, right? And so molecular dynamics, you can treat it as an input for your finite element approach. Molecular dynamics will only simulate these short length scales and time scales. It will give you the parameters which you then